So, I have already had an introduction, but I am Shiv. I'm going to talk about Iceberg, of course, it's Lakehouse meetup, but I'm going to take a different route, right? I'm going to look at how you can take your old, boring, existing databases like Postgres, right? The old, boring one that just works for most people for what it does, or ClickHouse, and I'm going to show you how you can take that database and make it support Iceberg, right? So this is not something where I will talk so much about Iceberg internals or something. I'll talk more about how it is coded, implemented inside Postgres or ClickHouse, and you can take those patterns and apply them to understanding how other DBs or other streaming platforms might do the same implementation. So very quickly, my areas of interest are distributed storage infrastructure, databases and streaming internals, and I am obviously influenced by my first job, which was at MySQL team. I was writing MySQL replication source code there, and the open source philosophy is something that is very dear to me. Apache Pulsar is something else that I have contributed a lot of code to, and in my day job right now, I help teams use ClickHouse or streaming platforms, time series, and all of that. I have my co-speaker in Saurabh Ojha. Saurabh, can you quickly introduce yourself?
Hi guys, I'm Saurabh. I work with Shiv as a data platform engineer in Nutanix. My areas of interest are database and streaming internals and less kernel feature. So I like to learn about open source and you may find me on LinkedIn. Thanks.
So just trying to be responsible and making sure that it is understood that this is my own view. I am not representing Nutanix at all in official capacity here. I think the previous talk was amazing, loved it, right? I can now very nicely build my talk on top of what you learned in the previous talk, right? So the first question is pretty much redundant. Have you guys used Iceberg? Anybody here who has used Iceberg, at least tinkering with it? Quick show of hands. Only one. I would hope more. Anybody who has run Iceberg in prod? Oh, wow, nice. We have a couple of hands. Perfect. And what query engines are you guys most familiar with? Quick show of hands. Sorry? Okay. DuckDB and? Athena. Okay. Nehal? Athena. Okay. I typically used to use Spark a lot to sort of learn around, and now I am trying to see how Postgres ClickHouse integrations can do. But how many of you here use Postgres? Let's see. More hands now. Anybody who's used Postgres? Okay, you guys know what Postgres is. ClickHouse? Very few. So I'll spend more time on ClickHouse, maybe less on Postgres. And finally, right? I am also trying to make sure that you guys are awake, because we are going to dive really deep into the code, into the weeds, and see how these database source codes are being implemented. Any open source contributors here? Or any aspiring open source contributor into databases? Aspiring ones, come on guys, right? And that's what I am trying to lead you to, right? Making easier for you to take some of the things that you learn here or pick up as references, maybe go talk to your AI copilot, ChatGPT or something, and start looking at that code, and then go ahead, let's do contributions. So this is the flow of my talk, right? Iceberg's appeal and adoption is pretty much done. I mean, I can't do a better job than the last talk, so I'll go through it quickly. I've actually hidden some of the slides that I had to represent that. The adoption is ever growing. We will talk about ClickHouse and Postgres integrations, and if time permits, we have an exhaustive demo, either some parts of it or in full. We will try to do demos for both Postgres Iceberg integration as well as ClickHouse Iceberg integration. And take away, like I said earlier, there was no better time to be an open source contributor in the database space, given you already have the spec and the APIs and reference implementations. There are other implementations in open source already there. All you have to do is pick up your favorite DB, look at the open source code, and try to hack around. If something doesn't work, fix it, add a feature that is missing, right? So I am absolutely loving all of this Iceberg story that way. So open table formats are becoming really foundational in modern data lake architectures, and I really believe that the adoption is low right now, but it's going to grow massively. Even so, if you look at OLTP, which is Postgres, or OLAP, which is ClickHouse, and in the previous talk, Bitman talked about Kafka Tableflow. Then you have Apache Pulsar doing Ursa. Rising Wave also has integrations. So why are all of these doing integrations with Iceberg, right? Because it's really popular. S3 tables announcing Iceberg support is also something that got a lot of mind share. So this is the time when you really should be looking into it if you are not, right? And I have made that point that I'm going to crack open the old and boring databases and so how Iceberg can be integrated there. Again, this is something that's been well covered. You have your data on S3 or any compatible object storage, open format, so less lock-in your data is there. Hopefully, less data migrations in future that we have to do. How many of you have a data migration story, sleepless nights? Only one? Come on. Data migration and cache invalidation are the two most notorious things in our field, right? Okay, more hands. Decoupling storage and compute has been a theme that's been playing out quite well. Started maybe back in the Snowflake implementation. That's been amazing. Snowflake is a beautiful product. By the way, Snowflake also has Iceberg integration to a certain extent now. You can manage Snowflake, use Snowflake to manage external Iceberg tables and whatnot. Schema evolution, time travel, partition pruning, ACID, most of these were introduced in the last talk, so I'll skip. But let's start the talk where we set base in the previous talk, right? This is the diagram you guys saw in the previous talk, right? So we start here, right? I'm not going to explain every piece because that was done previously. You have the storage layer, file format layer, table format, storage engine and compute engine, and catalog, right? So your data is already sitting, let's say, in S3 in a Parquet format, and you are using Iceberg table format. That's the prerequisite that I'm building this talk on, right? Again, your data is already on object storage you in Parquet format, and you have an Iceberg kind of thing. Where we will look at the code and architectures is in the top layer there, which is storage engine, compute engine, and catalog, and try to see how Postgres and ClickHouse code bases are evolving in those layers to integrate with Iceberg, right? But this is how your old databases were implemented, right? Your storage is very coupled with your compute, right? You expose something in the storage, do an enhancement, and your compute takes care of it. It's not like you can take a Postgres or ClickHouse today, take their storage engine, put a compute engine, and just start querying it, because it's very native to what ClickHouse does. And that's where Iceberg or another lake houses have done a revolution, right? And we will see that. And over time, people went into this data lake concept, right? So it allows you to put all kinds of data, structured, unstructured, semi-structured. Semi-structured meaning JSON. Unstructured could be, let's say, just text files, whatever, right? While the first set of databases like Snowflake and all were mostly around structures, most of the databases now have JSON support, so semi-structured also maybe. But in data log, you could pretty much put anything, right? The amazing thing about data lake was you see a stack of compute engines there, right? That's the nice thing that happened with data lakes, right? The problem was that you don't have a built-in storage engine that is taking care of all your files in S3, making sure it's in the right structure on the files, making sure it's being updated, maybe reorganized and all of that, right? Typically what your storage engine will do. And if you don't do that well, the compute engine has to do the right as well as read. And you'll have to turn a lot of knobs for every compute engine. So while it was very flexible, running it for a lot of teams with different compute engines was harder, right? You need a spec to bind everything together, and to this spec, all these compute engines come and talk. Then it would make more sense, right? And that is the birth of Lakehouse architectures, right? Now you see that your Lakehouse is named like lake and data versus house, something around that, right? That's my philosophy there. And you see, it's the best of both worlds in the way that you have a stacked compute engine in the Lakehouse as well. So we have derived that from there, but storage engine features were incomplete or missing in the data lake world, which was there in the warehouse world. So we are trying to get that here and trying to write a spec around table format and how storage engines should be implemented around these table formats, right? So that's what we are trying to do. So if you are trying to make a Lakehouse integration, again, in the old database, you have to rip apart the compute engine and storage engine. That compute engine, there has to be one more implementation where the storage is the Iceberg table, right? So this is what I'm talking about. So the old database of Postgres or ClickHouse will have its own compute engine that ties back, right? In this case, it is tying back to storage engine. These are tightly coupled. Here, we have a lot of compute engines derived from the data lake architecture, and then you have a storage engine with table format. This is where Iceberg is and gives a lot of things which storage engine can take advantage of, right? And I wanted to, I think the right side of the picture has been explained in the previous talk as well, but I wanted to put into context where all of these are, right? In this stacked diagram, deconstructed database, you see that table format is what all of this is about. Your metadata layer, metadata manifest file, manifest list file, and all of that. So now we've put that context. Now let's see how can you take a ClickHouse kind of a database, a Postgres kind of database, and extend it to support this architecture. Very few hands with ClickHouse. So I'll very quickly introduce in a couple of slides what ClickHouse is. It's a open source OLAP engine, columnar database, known for speed. So they have a benchmarking tool called ClickBench. It's live. It's completely open source backed. In fact, we have also put some PRs to improve some DB performance and all, but a lot of databases. You see here, right? All of these are systems that are being benchmarked here with a common data source and common set of queries. And a lot of different infrastructure and whatnot. And you see ClickHouse is on the top there. I mean, all benchmarks are lies, but it's at least open source. They take open source contributions that you do to make some DB, your favorite DB, look good. So some truth to it. Of course, with a different data set, with a different set of queries, maybe ClickHouse will go a little bit down, but it is for sure very fast. And this is the proof, right? So other thing is, you see the GitHub project, it's very popular, right? The number of stars and folk tell you a story. It's Apache licensed, completely open source, very easy to get started. If you know a Postgres or MySQL or any SQL database, getting started with ClickHouse is dead easy. You download the binary, make the same tables that you know of, columns, SQL layer, and all of that, right? So nothing fancy there. Very, very easy to get started, right? Very popular, open source, and very well adopted, right? And I don't want to paint a picture saying, you know what, it's all amazing in the database I'm talking about. No, right? Anybody tells me that, I don't buy it, right? So why should you buy why I'm saying, right? Let's see a couple of things that I probably don't like so much about ClickHouse yet, right? While I said it's very much like Postgres, it's also very unlike Postgres when you try to run it in production, right? It's columnar storage against the row storage in Postgres, and its columnar storage is obviously done for OLAP style queries. ClickHouse is really good at using every inch of your resource on your server. Very, very resource efficient. But what it is built to do from day one is mostly that you give it vertical scaling, bigger servers, and it will do really, really well, right? But people seem to, in this era, also like storage compute decoupling. That's coupled, like we talked earlier, right? In Postgres as well as ClickHouse. That in their cloud solution is being built. It's usable. It's actually quite well built. But in the open source version, it's not as easy. It's not easy to segregate. It's possible, but it's not trivial, right? But there is work going on in open source also for that, right? But what will help us build an Iceberg engine here is this part, right? A lot of integrations, and I'll take you through these integrations, how they are done, right? For what integrations are there, you can obviously go through the doc and look at it. You can just ask ChatGPT these days; it'll tell you. Hopefully, it's not hallucinating when you ask him that. But let's come back to the diagram, right? These are two diagrams that we saw earlier, right? This is the data warehouse coupled architecture, and this is your Lakehouse architecture decoupled with compute and storage. And this part is what is coming from your Iceberg side, and you have a host of compute engines that are Iceberg compatible now, right? If you had to take an old database like ClickHouse, right? This is taken from a wonderful blog that they had. I will have a link going further. But what are we doing here? How are we making their query engine? Query Iceberg data here, right? We take their, so you see all of this is what you see as Iceberg meta layer. You see the same manifest files that you saw earlier. Now you take their query engine, decouple it from their storage, make a different query engine. Hopefully you have an interface and one native implementation for their native storage engine, another implementation of compute engine for the Iceberg kind of storage. So you take the query engine, take the query, fire it on the query ClickHouse query engine, that's SQL. Then you go pull out the metadata. Once you have details about the metadata, by the way, the metadata is on S3, so you can also cache it hopefully here for quicker access. Maybe you have a write-through cache or something. Then you pull data from the data layer. Then you do your processing, and we will break it up one more level in the next few slides to see what and all we are doing here. But you do your processing on the data that you just got, and then you output the result, right? So the trick is that here we are making one more integration in compute engine that understands the Iceberg kind of storage. So this is what I am trying to put in for requirements. So if our database has to be hacked around, these are some basic features that I would expect should be there or has to be built. These databases like PostgreSQL and ClickHouse are built to query data that is sitting on the disk block attached to them. You have to obviously have a way to query data sitting on object storage. Maybe you can cache some parts of it, prefetch parts of it, or at least an option to do that, right? Will be nice. Iceberg can work with Parquet OS and all of that. I'm going to mostly talk about Parquet here. And maybe you can query Parquet, but all your data will never be sitting in Iceberg. You will have some data in Postgres, some data in some other places, maybe in a CSV file, a MongoDB, whatever, right? So you should have a way to get data from Iceberg in ClickHouse and some other places you can get those data, and you can join this and publish a report in your app, right? So that would be nice to have. Athena, a couple of people talked about it. Trino, kind of an engine to do that. For metadata files, you will have to make some data structures in your code in the query engine that we are writing new for Iceberg, right? And then there are a lot of good Lakehouse features that we have to write implementation for to call ourselves Iceberg compatible compute engine, right? And this is all the thing I am going to look at in the open source code, take you through the source code files inside ClickHouse to show how they are implementing it, and then you can use those concepts to understand how you can hack your old DB. So first off, in the requirement, we said integrations, right? To query anything on object storage, anything in Parquet, all of that. So let's look at the integrations in ClickHouse. ClickHouse has a huge number of integrations, right? So file formats, the number of file formats that it can talk to is humongous, right? Parquet, JSON, CSV, Apache Arrow, I have put some of these, but a lot of those, right? For instance, you see this sql.clickhouse.com. It's built for you to go play with some stock data sets. A bunch of data sets are there. Their queries are there. You can just go to sql.clickhouse.com and try these things for yourself, right? So if you execute this query on sql.clickhouse.com saying in the system table, I want to see how many of formats are there, right? And I did that and I saw a list of 73 file formats that ClickHouse can query, right? And you see our favorite Parquet there, right? Now, what I would also tell you is that all of these are obviously, no prices for guessing this, all of these are obviously not as performant as their own internal native format, right? But given the popularity of Iceberg architecture and Parquet adoption, they are working on making Parquet comparable with their native file format. There's a lot of work going in Parquet. We will see some bit of why I say that Parquet is quite well implemented, but there are more things to do there as well. I'll go into those implementations as well. But you see that you can query external file formats in ClickHouse. And by the way, you have a lot of aggregation types, SQL aggregation functions supported in ClickHouse again, right? Of course, the old databases, why we want to hack it? Because we want to use the good things there. So these are already there, right? I said I will look at the open source code of ClickHouse and encourage you to, after the talk, go back and look it up, and some open source contributions, please, after this talk at least. That would be a great takeaway, right? So this is ClickHouse code. You have an interface called input format, I input format, I for interface, and then you have all the derived classes for all the formats that I talked about. It's as easy as that, right? One more file format, just implement one more format reader, right? And we are talking about Parquet, right? We are more interested in Parquet than other things. If you are interested in other things, you can obviously look at the other. I mean, my IDE could not show everything together, but it's a lot of them. And you see, we talked about Parquet. So if you look at this file, you have all the Parquet reader implementation here. Here is your read method. You can go to the implementation of this method. This is just the interface. This .h file. If you go to the .cpp file, you will see exactly how they read Parquet, right? So, I mean, in the days of AI code readers and everything, I'm going to leave you there, go on the breadth level, but I believe that you can now go back and ask your favorite AI code companion to explain you the code there. Or if you are using this, these things are all Iceberg integrations in Postgres and ClickHouse are all very early. I'm not confident enough to use them in production right now, to be very honest. But I am very excited by looking at the code building up there, and I'm going to try and make some contributions there to make it work for my use cases. You can do for yours. That's the whole point of open source, right? We want to hack it to make it work for us. So we look at a bit of code, right? Let's come back one level and let's see how that format reader fits into the whole scheme of things when we look at the query engine querying Parquet. Right? Here is your Parquet reader. This is the file that I was talking about earlier, sitting alongside other implementations, right? TVSV reader, JSON reader, and all of these. These don't perform as well as Parquet, right? They are mostly for sort of very quickly querying things around and joining if required and all of that. You also have a CSV reader, by the way. So how does that whole thing work with the query engine? You pull apart the data from, in our case, object storage, through a Parquet reader, or you have some of the data in the local storage with CSV files and all with a CSV reader. Then you plug it into the ClickHouse query engine. From here, it would be pretty similar stack for their native engine also. And you process your data and output the results, right? And I said that Parquet is special because Parquet is more performant than other formats. By the way, they have a benchmarking website called something like Fast Formats. You can go to that website and see they have done their comparison on how their performance is across all of these file formats. And native obviously wins there as well, right? But Parquet is really still well done. I'll show you why some of the performance with Parquet makes sense. This is how they, if you know Parquet, you know that Parquet organizes data in columnar format. Within columnar format, they have, the data is put into chunks of row groups. Within every row group, you have columnar representation of data for those rows, right? Let's say 100 rows, 10 in each row group. For the 10, first column of 10, second column of 10, third column of 10 together, right? Something like that. So we can use the row group level to do parallelism here, right? In our query engine, we can spawn parallel threads, and this is configurable how many threads you want to do, max insert threads or something, or max threads or something, right? You can also prefetch the data because we are living in the S3 world or object storage world. We want to prefetch to be good with performance. You buffer all of that and then give it to the query engine in parallel, which will do its aggregation and stuff parallelly over those parts, and then merge all the result. If you understand the map reduce and all of those, you probably understand this as well, right? Or if you don't understand all of that, if you understand merge sort, right? You sort different parts parallelly, then you do whatever aggregate function you have to do there, and then you merge all the results. If there was a limit or something, you put that, and then you output the result. Sorry. By the way, new Parquet implement. So a few things are not there in Parquet that are yet to be built, but they are working on it, and it's open for contributions that you can suggest. They take care of parallelism on the level of row group, but within that, the column chunks of it, they I think don't parallelize right now. Even the pre-wire support, lazy materialization support, and all of those things, that's there in native format. That's not there for Parquet yet, but they are working on a new implementation of the Parquet reader that should hopefully have those. You can go to this blog and see a lot more about Parquet integrations, right? Then we said, apart from reading all the other file formats, you should be able to get data from all the different sources and join with this data, right? In different ways. So you can query data sitting in a ClickHouse from a lot of different places, like an Athena would do, or a Trino would do, right? From S3 of course, GCS, Azure, Blob, Kafka, MySQL, MongoDB, Redis, Elastic, a lot of those, right? Again, I'll very quickly show you some bits of the open source code of ClickHouse to see how this is being done. Sorry, before that, these integrations are something where you have a lot of flexibility as to how you want to do things, right? One is you have a function, a SQL function. For Iceberg, for instance, you have something like a Iceberg S3 SQL function that you can point to the S3 Parquet file or something, and then just query that, right? The query is forwarded to the external data source. You have table engines, right? These are storage engines. Storage engine, you have two varieties. One where you can replicate data, and locally, if you're going to query it a lot, keep the data in the local disk, so it's faster, but you're giving up some disk and compute for this replication. And you can also have a proxy table where you passively still forward the query to external data source. On the database level also, they have a lot of database engines. And again, on the database level, you have two types of engines. You can either replicate some of the data from external source locally in memory as a map and just join those things. I'll show you a use case. And you can also query directly. All the tables sitting inside this database will query this external data source directly, or it can be replicated on the blocks inside the ClickHouse server deployment, right? Or you can have a simple key value stored in memory sitting on the same memory space that ClickHouse is sitting on, right? We talked about table engine, right? If you want to go hack around the code for that, you have this interface iStorage. And again, you have a lot of implementations of iStorage. For every table engine, you have another storage implementation. For the native one, this is the storage implementation. For querying Postgres, you have this storage engine. For Kafka, you have this. For object storage that is of interest to us, you have something like this. So these are all the classes that you can go through. It will obviously, it's a table engine, so it will have methods like read from table, write into table, alter table, drop table, whatever. You will see all of those implemented for all the implementations of this storage interface that you see, right? So just look at this and the CPP files corresponding to the implementations. We talked about database engine, right? A bunch of tables. And this is of more interest to us for this talk because ultimately we are going to make a database engine within which all the Iceberg tables will sit. So database level itself, on that engine level, we are making an Iceberg compatible database inside. It's like your create database with data lake integration, and within that you have all the tables that are Iceberg tables. Right? For the database engine, you have idatabase.h. You can go to the class and look at the implementation of all the different database engines. Like you would expect, it works on group of tables level, not individual rows and columns. That's the responsibility of table engine. Core responsibilities are creating a table, dropping a table, all the table management kind of things, or iterate over all the tables, form a create table query and whatnot, right? But out of all the implementations, the one thing that we care about for this talk is this implementation. So they just implemented one more implementation of this interface, data lake, database data lake, right? This is where all your implementation for Iceberg sits, right? So if you have Parquet, if you have Iceberg, if you have data and object storage, all of those integrations are there in ClickHouse. It has to come together to do Iceberg. But the building blocks are there to a certain extent, right? Let's very quickly see how we can read data from, like, you would be like, I see all this code and everything, but take me one level back and show me how will I read and write, right? What will my architecture look like, right? This is again taken from one of their blogs, which I have linked below. They write really good blogs, technical blogs, so you can go look at that. But you put all your data inside S3 or any object storage in the Parquet format, and you put Iceberg metadata and everything. You have a remote Iceberg. Let's say you wrote it with Spark or any other engine that you can write from. And then you have a method called SQL function called S3 cluster, or an table engine also similar thing, which will dump all of that data here that you want here, right? Or you can have an S3 queue also on top of it, where incrementally as data is coming here, it is also copying to ClickHouse. So you can query it remotely sitting in object store. You can also copy it here, I said, right? You can do it using these functions. This ClickPipe is their, ClickHouse cloud feature. You can do ad hoc query, or you can copy things here, right? Now, sometimes you don't want to get all the Postgres data to query. I mean, I have tried Trino, and I don't think that you can take two huge different databases and join, it will work seamlessly every time. No. I mean, there are problems. So what you want to do is maybe take a bunch of data, put it in memory on the ClickHouse process itself as a dictionary. Dictionary has a lot of different implementations. For the purpose of this talk, let's say it's a simple key value structure, right? So I'll actually take an example to show that, right? So let's say you have to prepare a report. You have user ID and user names. ID is there in your analytics database, name is not there. User ID and name mapping is there in your operational database. What you can do is, your operational database, let's say Postgres, for instance, you can take only those two columns, put it inside the dictionary, user ID, user name mapping here, and when you query data, either from remote or a copy of this inside ClickHouse, you can join with this. So in the report, you say, I am making a dictionary with user ID and user name sourced from Postgres, which sits on ClickHouse server memory space, and then you use the ID name mapping, put it inside the data that you got from your analytics engine, and merge them on memory there itself, right? So you don't have to go to Postgres to get that mapping all the time. This is very performant. Or if you have to join with two huge tables, then you can't put that in dictionary in the memory space. It will become very big and troublesome, right? You can also do that, but this is also good for some use cases. How do I write? The native write support in ClickHouse is still not there, right? It's being worked upon. And one of the problems is that if you look at Iceberg, SDKs and everything, Iceberg, Java, and maybe Python and Rust are well beyond being used a lot of places. The Iceberg CPP SDK is still very nascent, very few features. So, I mean, it'll take some time to natively be able to write two Iceberg tables from ClickHouse, as is with other C++ engines. But what you can do is what I described earlier. You can keep your Iceberg table, somehow it landed there. You can back it up using S3 and S3 cluster or ClickHouse, and in ClickHouse you have that, or you can remotely again query, right? The other way you can do that today is have a Kafka kind of a thing, and you do a double write approach. You write it to Iceberg as well as ClickHouse. Here you do native query. Let's say this is the hot layer, so you have all the recent data here. Maybe you have a 1 month or 1 week TTL here for recent data, and for cold data you use this, right? Let's say in this approach you have all the data here and only the recent data here. Storage in S3 is cheap, so you can do all that. But if you still care about not duplicating data, what I would like to see in the implementation in future, and some people in community are already talking about those, is you can today set a TTL on ClickHouse, yeah, here, right, on your tables, and you can say, as data gets 1 month old, can we offload it to Iceberg? That is an architecture that people in community are working on. And I said in the requirement that we should have support for other Iceberg things, right? I'll not go into deep in this. I'll quickly run through this, giving you some links. But you have the catalog support, right? The node, ClickHouse server node can talk to the catalog, and then it can talk to the meta and get meta information. It can also cache meta information here, and then using that meta information, it will go to the right places to fetch the data, right? About catalog again, very quickly, you have a iCatalog interface in the ClickHouse code base, and you have a lot of implementations there, and a bunch of them like Nessie and stuff are not there. They should come up. I have done a demo with REST catalog that we will show you. Right? I talked about metadata caching. This is the file that we are talking about here. Right? So, like I said, experimental, still building, get involved. I really think this is the time when a lot of deep tech products are being built from India. I think E6 data team has a lot of people here. They are doing a compute engine. So if you are interested to go into deep tech and do some things, even if your job doesn't allow you and all of that, you can look at the open source code bases, try things out, test them, put PRs, put issues and all of that. So read-only queries for night, no native writes, but there are other ways to do this. We will show you the demo. We will use Spark for writes and ClickHouse for reads. Catalog support I talked about. Time travel, this is the PR link that I have put. After the presentation in the last slide, I have put a QR code. You can download the slides from there. It's available on my GitHub, and you can see these links for yourself. Partition pruning, schema evaluation, all of those are there. We also have those covered in the demo. If we have time, we can show all of them or only a part of them. Metadata caching, I talked about. Here is the PR. I also showed you the code. Right? And the roadmap is out there in the open. You can look at the roadmap. I am talking about writing into data lakes for a long time. This is the GitHub issue for it. This is still not done. Some other things are done. So in 2025, ClickHouse has this roadmap. You can go look at it. A lot of PRs are still in building phase. A lot of things are still pending, not done. You can go hack around those. And it's not only the main ClickHouse team implementing these things. There are also alternate implementations being worked on. There's this company called Alternity. They are making S3 storage, Parquet file, all of that is already there. I told you in the beginning that tiering with storage and compute segregated, both of them scaling independently, is not a strong feature of ClickHouse open source. So they are trying to make this compute swarms. These are compute, stateless compute layers that you can just put up on Kubernetes, add more replicas to it, and you will see that queries will be faster. I didn't want to dedicate a lot of time to this again. So I have left you with announcement blog. This is very, very decent. And GitHub repo for examples and all of that. Right? I talked about a lot of theory. I want to show you that some of these are there in the demo and they work. So Saurabh will be doing a quick demo of ClickHouse Iceberg integration. But if you scan that QR code, you will see the demo.
If you want to run the demo, you can close the demo and run the scripts. Quickly go into the setup. we have a compute layer where we are using Iceberg for writing tables and ClickHouse for querying those. We have a storage layer where we are using Nutanix for SQL compatible storage, and we have a catalog layer which is Hyper-OS catalog. This is the default implementation that you get with Iceberg. So in the interest of time, what I have done is I have already loaded the tables on my IO. When you fire up the retrofit, what you get is a Lakehouse container with scripts table which has around 2.5 million rows in it. And then I have transferred that as a marquee on my IO console. Let's quickly have a look at how it looks on your S3. So this is where my file that I generated from ClickHouse to RK and this is where my Iceberg tables are. So I have created two tables, the same schema but different partitioning schemes. This is a partition table. This is the payment type field. Trips unpartitioned is flat. There is no partitioning done there. So I will quickly show you one of the features, that is partition pruning. So how many of you know here what partition pruning in Iceberg is? So basically what it says is, if you have an SQL query, say select star from something where a field equals something, then partition pruning says that you should be able to skip data files that do not have that field. That is what I am going to show you here. I'll quickly go to the ClickHouse container, and before that, you can also, as Shiv mentioned, you can query ClickHouse like files on S3 using ClickHouse functions directly. You can use S3 function and Iceberg S3 functions, all those. Yeah. So partition pruning is an experimental feature, and your Iceberg database as well is an experimental feature. So I'm going to enable that in my container. What I'm going to do is I'm going to create a database. So as Shiv had mentioned about database engine earlier, data lake catalog is that engine where you provide it with the type of the catalog. So REST catalog is what we are using today. Storage endpoint where your actual files are lying, and the endpoint of the REST. I'm going to create this database. Once this database is created, you can actually
you can do some.
Achha.
Or you can zoom.
Is it visible now? Yeah. Okay. So what we have essentially done is we have said ClickHouse that create a database demo and point it to the REST catalog and the storage endpoint of my Iceberg tables, and it is querying those tables that we had created and placed in my S3 earlier. Now what I am going to do is I am going to show you how partition pruning works. So it is an experimental feature, so I am going to enable it. I will be running the same query, select the count of all the rows from the trips table where payment type is 1. So we had two tables, one was partitioned, another was unpartitioned. I'll run the query on both the tables, and then we are going to have a look at what the differences were in the run of those queries. So I've run it quickly on the partitioned one. Now I'm running it on the unpartitioned one. So when you run a query, ClickHouse stores some data about that query run in your query log tables. You can go ahead and you can, it has a lot of fields. In the context of partition pruning, what I'm going to show you is how many rows were read, how many bytes were read, and how many files were skipped. So this is the query. So in the case of Iceberg partition table, let's quickly have a look at the number of files that were skipped, number of rows that were read, and number of bytes we had read. So what are these 3 skipped files that we see here? So whenever a query is run in ClickHouse, basically a profile event is emitted, and this is the name of that event, Iceberg partition prune files, and this is a counter which increments every time you skip a file, skip a data file. So if you go to the trips data directory, you'll see we had 4 directories, payment type 1, 2, 3, and 4, and we were able to skip all the queries that, all the folders that did not have payment type 1 in it, that are 2, 3, and 4. And since these directories individually had only 1 file, we have to skip the total of 3 files. Now, if you run the same on the unpartitioned table, this is the query ID for that. What you see is we have read all the rows, basically this is the entire data set. We have read a lot more bytes and we have skipped no files. So partition pruning helps you skip data files, and as you know, this IO is expensive. You have to reduce the amount of files that you read. This is an Iceberg feature that comes in handy, and ClickHouse is able to do that pretty well. Yeah.
So, okay. So the demo page that you saw, that has demo for time travel as well, and you can go and check out the demo yourself. You can try those. If there are issues, you can file a issue of the GitHub repo. We will take a look at it and help you run the demo if you want. So we talked about ClickHouse, right? We saw some requirements and we said, how can we achieve these things with ClickHouse, right? To really make the pattern and so stay true to the theme of the talk, hacking open source databases, we have to see at least 2 databases, and we have to see the patterns around those, and we can use those patterns generically then to any database or any implementation that you are trying to do, right? So let's look at Postgres, right? How does the extension in Postgres work really, right? There's a core Postgres database, harder to get code into, but very, very stable, right? So extension is the way to extend Postgres to make it do a lot of other things that's not there in the core database, right? Query foreign data, like foreign data could be sitting on S3, it could be in ClickHouse, it could be in Mongo, whatever, right? So you can do all of that. You can make user-defined functions, you can make custom index, a lot of those, right? And proof of the pudding again, Postgres is proper OLTP, right? Transactional database. It was never meant to do time series database, but timescale is extension where you can do time series. Citus, again, Postgres is typically not a distributed database in itself, but mostly a master-slave, active-passive kind of setup. But with Citus extension, you can distribute the compute and have a distributed SQL on top of Postgres. GIS for geospatial data, and we will talk a bit about pgduckdb today, right? So that's why that's there in the list as well. But you can basically create an extension. A lot of extensions are out there. You can use those extensions as well, or you can create it yourself and add that extension into Postgres. There's a contrib directory where you put all of those. And there are other ways to extend the database, right? Outside the core. Foreign data wrapper we talked about. You can do that with Parquet FDW for Parquet, ClickHouse FDW for FDW is foreign data wrapper. ClickHouse foreign data wrapper, ParadeDB, Speech Analytics, and all of that are foreign data wrappers. Postgres also recently did one nice thing which opens up for a lot of innovation, is similar to the storage engine interface that we saw in ClickHouse, right? So what they did a few years ago is they took their original storage engine, which was coupled, scattered code and all of that, put an interface to it, put their original implementation behind it, so other people can go and make other kind of storage engines, just implementing that interface, right? MySQL also has something similar called handler interface already, right? And this is where you are not keeping data inside Postgres, where here you are keeping that columnar data or any other storage engine inside Postgres data, Postgres disk, and then here you are just querying from foreign places like S3 and stuff, right? And you have proper OLTP in Postgres, right? So to do Iceberg, you need a columnar storage, you need a way to, have vectorization to take advantage of SIMD enabled CPUs there. Postgres has Volcano model. For every row, it will take and pass it around just to access that one single column for your aggregation. So you need a compute engine that has vectorization. So what people are doing these days, there are a lot of projects that you will see on GitHub, open source projects, where people are taking DuckDB. In the previous talk, we had some introduction to DuckDB already. So that's useful. Now you can take DuckDB, the embeddable part of it, the library part of it, put it inside a Postgres extension, right? So now it is operating as a code block inside the Postgres memory space. And a lot of projects are just doing that to make analytics possible on Postgres. And DuckDB can do a lot of things like read Parquet and Iceberg and all those things on S3. Writes is still yet to come, again C++ engine, so that ecosystem is not there. If you want to do heavy computes and can't do on one node, because Postgres is one node, you put DuckDB inside that, so still one node for analytics, not enough. Use MotherDuck as a hosted service to do analytics on top of Postgres data sitting inside Postgres or outside on S3 or whatever, right? By the way, DuckDB syntax also works closely with Postgres syntax, so that's nice. Like I said, DuckDB is wrapped inside Postgres, and DuckDB has a lot of these functions. So as soon as you make this whole extension with DuckDB sitting inside the Postgres memory space, you have access to all of these functions of DuckDB from Postgres SQL query layer. So I'll invite Saurabh Ojha again to take you through the internals of Postgres extension and show you some bits of demo.
So what we look at So what we are going to look at is how PGWD is able to divert the execution of a query from the standard Postgres execution path. So before that, a small primer on what hooks are. So whenever you have a query, it goes through certain stages, and that stages are parsing the query, planning the query, and then executing that query. Parsing is where you actually take the query, parse it, convert it to a parse tree. Once you have parsed the queries, you have to select in Postgres, you have to select the minimum cost plan that will go ahead and execute the query. That is where your planner comes in, and it goes through a bunch of cost estimations and finds you the minimum cost plan that your query will use. Executor phase is where you actually go and execute your queries. So what hooks are? Hooks are a way of that Postgres has provided so that you can go ahead and you can inject custom behaviors across this path at certain stages. So you have multiple hooks. For those who have done web development using Spring Boot or maybe Golang, you can think of hooks as filters or interceptors. So planner hook is one of the hooks that Postgres provides, which can be used to divert the execution path of the query just before you start planning. So what PGWD does is it takes the parse tree that you get from your standard Postgres parsing, and then it uses the planner hook and it injects its own code. By the way, planner hooks are global pointers in Postgres.
method pointers, and you can do stuff like hook chaining as well, where once you are done with your hook, you can replace it with the previous hook. Executor start and executor end hooks are in your executor phase. These are used by PGDuckDB for snapshot internals. Explain one query is an interesting hook that Postgres provides, so that the custom execution that you do, you are able to provide better explanations for that. So if you have run, say, explain select star from some table on Postgres, you get some output where you see what kind of plan was followed, what kind of filters were applied, what kind of scans were done. Explain one query hook helps you delegate that to a custom method or a custom behavior, so that you are able to provide more details. Why this helps is because Postgres might not know what DuckDB execution is doing with the query. So it makes sense that your DuckDB execution is the one that provides you with the explanation of the query. So I'll quickly show you, by the way, this code has been taken from PG Mooncake. So if you see in the DuckDB init hooks function, we are assigning the planner hook to a DuckDB planner hook, and same with the other hooks. We'll have a look at how query stealing is done at the planning phase. So DuckDB planner hook is a C method, and it internally invokes a C++ method. What it does is it checks whether the planned query tree that you have, whether it is even requiring a DuckDB execution in the first place. So this needs DuckDB execution method. It goes ahead and it checks whether the query contains any DuckDB identifiable tables, or whether it contains any functions that are a part of DuckDB execution. So the functions that you saw before, read, parquet, Iceberg scan, all those are checked here. And if that is the case, it straight away returns a DuckDB plan node from here, which is a plan statement, and it gives you a minimum cost plan for executing that query, instead of going ahead with the standard plan. So this is where your actual query stealing is happening, and a new plan is returned instead of your standard Postgres plan. So far what we have looked at is how PGDuckDB is able to provide you with functionalities of reading tables and Iceberg tables and Parquet files, which might not be on your local disk, which might be on your S3. But what is lacking in PGDuckDB is the ability to write these Iceberg tables. That is where your PG Mooncake comes in. PG Mooncake is, in a way, you can say it extends on the functionality of PGDuckDB by providing you with a columnar store. And this columnar store can be on your local Postgres, where your local Postgres is running, or it can be on your S3 as well. It can be on an object store. So what access method interfaces are, Shiv had already explained. So basically, Postgres had coupled its storage layer earlier, and then decided if someone wants to create a new storage format, they should be able to do that. So access method interfaces defines how you actually store data on your disk and how you are able to access that. There are two parts of access method interface. One is your table access method, and one is your index access method. What we are going to look at is table access method. PG Mooncake basically implements these table access methods and creates a columnar store. So what it has done is it has now created an ability to write these Iceberg tables using a table access method, using a columnar store that implements the table access method interface. And for now, it says it can write delta tables, but a support to write Iceberg tables is coming very soon. It's expected to come out in June. Yeah, so you can create, once you have the PG Mooncake extension in your Postgres, you can use this column store table access method to create your table. If you have an S3 bucket configured, all the data goes to that S3 bucket. If not, it stays in your local disk. So taking a step back and looking at how the operations of a company looks on day one. So if you are a startup or a company and you have your Postgres running, it is going to serve all your user application queries. And if you have some ad hoc analytics, 2 minutes, okay. If you have some ad hoc analytics on top of that, maybe you're able to run it directly on Postgres. But as the usage rises, this is not ideal because Postgres is not meant to run your analytical queries. So how would your operations look like on day 2 and 3? Using an extension like PG Mooncake, on day 2, you can simply plug in the extension and you could delegate that OLAP queries to DuckDB. Maybe that is not performant enough for you. You go ahead and create a replica and you install an extension over there, and then you're able to improve your OLAP style queries performance. So another plugin here, Crunchy Data, allows you to logically replicate changes from a Postgres table directly to Iceberg. And as you can see here, it creates your Iceberg tables automatically. It also has automatic compaction and it periodically flushes the data to your Iceberg. So I think we have run out of time, so I will not be able to show you a small demo for this, but it's pretty straightforward. You can clone the repo, all the scripts are contained, you can run and you can go through the README files and execute those. Quickly handing it over back to Shiv for wrapping the session up.
Right. So, yeah. The last slide really. So, what is good about this is you have native storage engine and compute engine of these databases like PostgreSQL and ClickHouse, which will work really well. I don't think the Iceberg implementations will start working better than that. That's my personal opinion though. But what you get with these extra integrations is you get open architecture, hopefully no more migration and all of those things. And one of the ways that I think of using it is that if you are committed to your current query language, your Postgres query language or ClickHouse is spread across all the applications inside the big company, it's very hard to go get it changed everywhere. Maybe just to do a POC, right? Why should you buy anything without a POC, right? So do a POC yourself. In Postgres case, for instance, you have the Postgres DB, make a replica of that DB, put Mooncake extension and stuff there, and do your analytics using the same applications there for your POC. And like I said earlier, great time to be a builder. If you love hacking open source code, hopefully I've inspired some of you to do that. Like I promised, here is the QR code for the slides if you want. And this is the link. This is my LinkedIn if you have questions. Can I take a few questions? Yeah. Sorry, we want to come here. Yeah. Any questions? A lot of content, but you can go back and refer it again.
It's more specific to...
Louder? Can you be louder, please?
This question will be more specific to Iceberg. So how do we, handle the dynamically changing schemas? How do we store it?
So, are you talking about schema evolution?
Yes.
We have a demo for that. We couldn't show you that. So, if you go to the demo page, it will show you that. But it right now, ClickHouse doesn't do writes, right? So it is not doing your. Actually, it can. Schema evolution is there in ClickHouse. So schema evolution, you want to know how it does it, right? Sorry, you want to talk about it?
So schema evolution is quite restricted in the Iceberg side. Basically, what you are allowed to do is you are allowed to add a column, delete a column, update a column. All these changes are by the way done in the metadata layer. It doesn't touches your data layer until and unless you are going to insert some new data in it. And within schema evolution, if you are going to change the type of a column, data column, you are restricted there as well. You cannot go ahead and change an integer to string or integer to float.
you can promote the types within the class of the variables. Integer can become a long, float can be promoted to double. This is all the schema evolution features that are present as of now. With respect to ClickHouse, whatever changes you make, ClickHouse is able to get that changed quickly because it communicates with the REST catalog. And your latest schema is then available in your ClickHouse. Does that answer the question?
So you talked about logical replication from Postgres to Iceberg using Crunchy.
Yeah, can you be louder, please? Yeah.
You talked about logical replication from Postgres to Iceberg in Crunchy data warehouse.
Yes.
Is there any other alternative from Postgres to Iceberg other than Crunchy warehouse or dumping into S3 directly?
So I follow Crunchy Warehouse quite well, right? This guy Marcos Lott who writes amazing blogs and stuff. So they are actually quite ahead. So I take inspiration for a lot of ideas from there. But if you want to use something else, like for instance, we talked about Mooncake, they are also building logical replication where you can replicate from stock Postgres to Iceberg columnar on your S3. So that is coming up, but that S3 data is still in Iceberg format for this implementation, both of them. Right? Do you want to keep it on S3, just not in Iceberg, or?
No, like all S3 on Iceberg. So if you have
Okay.
the reasonable face, if you have highlights, or an issue.
Okay, can you be louder again?
So if you have highlights,
Uh-huh.
there's a challenge which I'm facing on that horizontally the visual scaling is not good. Challenging.
Did you get it? No, we can't hear you properly. Can you?
So if I want to do a logical replication from Postgres to Iceberg on S3,
Yes.
is there any connector which is available, like if you're on it?
Yeah, I mean, we were talking about the Mooncake extension, right? You can add that extension and do it. Like it's not released yet, but we took the Crunchy example to show you how it can be done, right? But that implementation is not there yet. It's there in their roadmap.
The Mooncake is actually in development phase of that. Mooncake is what they're calling it. It will be amazing. So that will be able to create that access to Postgres and stream to the.
Any other methodology you're aware?
So I left some links with PostgreSQL integrations, right? You can explore the other three also, but to my knowledge, all of these are pretty much beginning of development right now. I don't think there is a way to just replicate in production kind of scenarios right yet. Maybe end of year or something, you should have something usable. For now, you can use Kafka or something to just push things through another engines and all. You take the CDC from Postgres, put it into Kafka or similar something, and then from Kafka you write it to maybe a table flow, maybe a consumer like Spark or something to just put it there. Any other questions? Okay, yeah, thank you.